You know, everything you see, everything you touch, even the air you're breathing right now, it's all made of stuff. But what is that stuff really, like fundamentally? Well, today we're going to be detectives. We're opening up a case file to investigate the hidden nature of matter itself and crack the code of how our world really works. And it really is a simple idea, but when you think about it, it's pretty profound. The screen you're looking at, the air in your lungs, even the most distant star you can imagine, it's all matter. It is the universal building block for, well, everything that has mass and takes up space.
So that brings us to the central mystery, the big question that scientists and thinkers argued about for centuries. Is matter this one, solid, continuous block, kind of like a piece of wood? Or is it made up of countless tiny, separate particles, more like a handful of sand? To figure this out, we've got to follow the clues.
All right, our first clue comes from a super simple experiment, something you could actually try in your own kitchen. We're going to investigate what I like to call the case of the disappearing salt. Let's see what it tells us. Okay, so picture this. You've got a glass of water, and you mark the water level really carefully. Now you take a spoonful of salt, which definitely has its own volume, right? And you stir it in. You stir and stir until, poof, the salt just vanishes. But then you look closely at that mark you made. So what in the world just happened? The salt is gone, but the water level, it didn't rise at all. That seems impossible, doesn't it? How can you add something to a container without the level going up? This right here is a massive clue. And this leads us to our first major breakthrough in the case. Matter is not a solid block. It's particulate. It's made of tiny little particles with empty spaces in between them. The salt didn't actually disappear. Its tiny particles just slipped right into the gaps between the water particles. Mystery solved.
Okay, so our case is definitely building. We know matter is made of particles. Awesome. But our investigation is far from over. I mean, how small are these particles? And are they just sitting there? Or is there more going on?
To get a sense of just how small we're talking, check this out. Just 2 or 3 tiny little crystals of potassium permanganate, it's this really vibrant purple stuff, are enough to color this entire massive volume of water. We're talking 1,000 liters. How is that even possible? I mean, the only way that could possibly happen is if each one of those tiny crystals contains millions of even tinier particles, and each one of those particles carries that purple color. They just spread out, dividing and dividing until they're literally everywhere. The particles of matter are, well, they're smaller than we can really even imagine. All right, so they're ridiculously, unimaginably small. Got it. But are they just sitting still? Think about this. You have to get right up close to an unlit incense stick to smell it, right? But light it up, and that smell fills the whole room in no time. Same thing with hot food versus cold food. What's actually changing? The answer is a process called diffusion. You see, particles are not still. They are in constant random motion. They have what scientists call kinetic energy. And when you heat them up, like by lighting that incense stick, you give them more energy. They start moving faster, spreading out way more quickly, and mixing with all the air particles completely on their own. Okay, let's take a second and review our case file. What have we figured out so far? We know particles have space between them, we know they're incredibly small, and we know they are always moving. But there's one more crucial piece to this puzzle. They also attract each other. This force of attraction is what holds everything together, and it's the absolute key to our next big reveal. And now it's time for the big reveal. These 4 simple rules we've just figured out, they're not just random facts. They are the keys that unlock one of the most fundamental concepts in all of science, the states of matter. That's right. A solid, a liquid, and a gas, they aren't fundamentally different kinds of stuff. They're just different arrangements, different energy levels of the very same particles. It all just boils down to the spacing between them, how fast they're moving, and how strongly they're attracting each other. And this table here just lays it all out perfectly. In a solid, that attraction between particles is super strong, so they're locked in place. They can only vibrate. That's what gives it a fixed shape. In a gas, on the other hand, there's almost no attraction, so the particles just fly around like crazy at high speed, filling up whatever container you put them in. And liquids, well, they're that fascinating, flowing middle ground. Every single property you see here is explained by that particle behavior. So, we've cracked the code on solids, liquids, and gases. But what happens when we start mixing particles from different substances together? Our investigation continues as we dive into mixtures.
So when you mix things, you usually get one of two results. You either get a homogeneous mixture, like salt water, where the salt particles spread out so evenly you can't even see them anymore. It's totally uniform. Or you get a heterogeneous mixture, like oil and water, where the particles just refuse to mix, and you can clearly see those different layers. But there's this really interesting in-between category. Let's take milk, for example. It looks perfectly mixed, right? Totally uniform. But it's actually something called a colloid. Its particles are too tiny to see with your eyes, but they're just big enough to do something pretty cool with light. And what it does is called the Tyndall effect. Have you ever been in a forest and seen those beautiful, distinct sunbeams shining down through the trees? That's the Tyndall effect, right there. In real life, the sunlight is being scattered by tiny particles of dust and water droplets in the air, which makes its path visible. That forest air is basically a giant natural colloid, just like fog in your car's headlights. Okay, for our final section, we've got one last twist in our investigation. It's a phenomenon that ties particle motion, energy, and temperature all together into an experience we literally feel every single day. Let's look at the science of vanishing. We're talking about evaporation. Now, this isn't the same thing as boiling. Evaporation can happen at any temperature. It's all about the particles right there on the surface of a liquid. Just through their random motion, some of them gain enough energy to break free from the forces holding them to their neighbors, and they escape into the air as a gas. And the cool thing is, we can actually manipulate this process. In fact, we do it all the time without even thinking about it. When we hang up wet clothes, we spread them out to increase the surface area. We all know they dry faster on a hot, windy day. Every single one of these actions is just helping more of those surface particles get the energy they need to make a break for it. But here is the coolest part of all, and I mean that literally. To escape, those particles need energy. So where do they get it from? They steal it. They absorb heat energy from their surroundings, from whatever they're touching. And that's why evaporation actually makes things cooler. It's the whole reason sweating cools you down, and why putting acetone or nail polish remover on your hand feels instantly ice cold. And that right there brings our entire investigation full circle. From a simple spoonful of salt dissolving in water to why we wear cotton clothes to stay cool in the summer, the world just makes so much more sense when you realize what it is. Just countless tiny particles, all in constant dynamic motion. So now that you're in on the secret, what other everyday things can this one simple idea explain?